Hello and welcome to today's webinar, which is on designing low-power IoT applications. And these are questions and answers with our expert panel. My name is Jeremy Cowan. I'm editorial director and co-founder of IoT Now, and it's my very great pleasure to be your moderator today for a webinar with a slightly different format. This one is based around your questions and answers from our experts. We had far more questions that we could deal with in part one of this webinar a couple of months ago. So we felt it was time to come back to them today. Thank you all for joining us, wherever you are around the world. We've got a very topical discussion for you on LPWA, brought to you with Sierra Wireless and Altair Semiconductor. So the first thing I want to do is to welcome our speakers. In order of appearance, they are Gus Voss, Chief Engineer, Technology Standards at Sierra Wireless, and a big welcome to you, Gus.
Well, thank you very much. It's great to be here.
And our second speaker will be Dima Feldman, who is Director of Product Management at Altair Semiconductor. Good to have you here too, Dima.
Thank you, Jeremy. It's great to be here.
And finally, I'm delighted to say we'll hear again from Sierra Wireless's Brian O'Flaherty-Wills, who is Senior Director of Product Management. A warm welcome to you, Brian.
Thank you, Jeremy. Good day, and thanks a lot for having me.
Now, don't forget, everyone, this webinar is being recorded, and from tomorrow you can access the audio and slides via our website at iot-now.com. As with all our webinars, we want to know what you think. To answer that, we have a poll which comes later, and at the end there's a chance for you to question all our speakers. So you can start sending me your questions right now, and I'll put them to our panel at the end. All you have to do is click on the questions button and type yours into the window. Finally, if you're having any technical issues with audio or slides, you can also use the question window to get advice from our tech support team who are ready and waiting. Today's webinar is therefore for anyone thinking of deploying a battery or solar-powered application or who just requires very low power for their IoT deployment. Okay, the first thing we need to do is have a quick recap on LPWA networks, and then we'll go to our audience poll to get your views before looking at questions that we didn't get to from the previous webinar. And then we'll go to our live questions and answers from today. So, Gus, can you start this recap for us?
Absolutely. Thank you, Jeremy, and hello, everybody. So, yeah, we're going to start with a recap here. Oh, we're getting some feedback. So, yeah, that sounds better now. Okay, so, yeah, we're going to start with a recap. Although the first three slides here are actually new, we had so many questions about 5G, we really wanted to tackle this topic first. So the first question really is, well, what is 5G? It's actually not a straightforward question to answer, so I wanted to give some background first. So the International Telecom Union, or the ITU, is a standard organization which sets requirements for the different classes of technology, like for 3G and 4G, they set those requirements. And they're doing the same for 5G. So there's a project called IMT 2020, which outlines those use cases and requirements. And as you can see in this slide, the use cases are very diverse, but basically fit into three buckets. The one bucket, which we're talking about mostly today, is LPWA. But there's also two other buckets, one called Enhanced Mobile Broadband, and then the other one called Critical Communications, which has this ultra-reliable and low-latency communications. So unsurprisingly, with such a diverse set of use cases comes a very diverse set of underlying requirements. And if you look at these requirements, you can see that some of them are in polar opposition, where you've got LPWAs needing lower cost and really don't need high data. You've got enhanced mobile broadband, which wants really, really high data rates. So it makes it very difficult to design one technology that fits all of these use cases. So 3GPP has a plan to deal with this. This is the standard organization that is defining 5G, that basically 5G is now more of a system, and it's a system of 5G components, where each of these components will basically support these different use cases. So for example, for LPWA, the 5G component will be either LTE-M and or NB IoT. For enhanced mobile broadband, we have the new access technology called NR, and or you can deploy LTE. For critical communications, there's a new core network being defined, which will support things like network slicing better, which is what's needed for the ultra-reliable and low latency communications. So on the right, we've got these list of these 5G components. As you can see, some are evolved and some are new, but all are part of the 3GPP Release 15, which is being defined right now, expected to be completed in June. All will be labeled with that 5G logo. Hopefully you guys have seen it. And all will be submitted to the ITU or in this IMT 2020 project for evaluation in 2020. So the key message here, though, is that LTE-M and NB IoT are 5G components and are the 5G technologies that support LPWA. Okay, so now moving on to more of the review. LPWA, not your legacy cellular. This is a new category of cellular that hits these 4 Cs that traditional cellular can't meet. And that's because LPWA applications, of course, use much lower data rates, very latency tolerant, and send much less data per month. You know, you're talking about tens of kilobytes per month versus gigabytes. So there's 2 to 3 orders of magnitude difference there. And this allowed those engineers to create the 4 Cs that you see on your screen. Specifically with respect to NBIOT and LTE-M, as you can see, these are 5G ready or on the path to 5G. In general, NBIOT has lower data rates, limited mobility, so it's ideal for sensor applications, where LTE-M is higher functioning, has higher speeds, also supports full mobility and real-time applications such as voice. But you need to consider beyond the 4 Cs. Application developers need to look to see what kind of coverage, for example, they have. Maybe they don't have an LPWA coverage in certain areas, so they should consider 2G fallback, or maybe they need to consider whether LTE-M and NB-IoT are supported everywhere, so they might need multi-mode support. If you're size constrained, SIMs are often a good way to reduce size by embedding the SIM into the module. These are all considerations that you need to consider beyond the 4 Cs, as well, of course, as making sure that your devices are field upgradable, not just for security patches, but you'll see there's some really interesting Release 14 features, as well as the Release 15 features of the future. And with that, I'm going to throw it over to Dima to talk about power.
Thank you, Gus. Yeah, thank you very much, Gus. Before going to more question and answers, and since we are dealing with the low power in this webinar, we wanted to review the techniques that are needed, or the 2 main techniques that we get from LPWA in order to achieve low power in cellular devices. One of the techniques called PSM, or power saving mode, is very commonly used in the devices that go to sleep for quite some time and wake and send their data. It's typically called the devices with device-originated traffic. You could think of various sensors that wakes up and send the data. The other method called EDRX, which stands for Extended Discontinuous Reception, is the method where device goes to sleep for a shorter period of time, typically seconds to tens of seconds, and then it can wake up and listen to network paging. For example, it could be a tracker device and network wants to know where the tracker is, it could send a paging message asking, hey, where your location is, and then device could answer like our regular phone today. And once we look on those two methods, we oftenly been asked, could you be more specific which method should be used for each device? And to answer that, we came basically with two metrics. One is the application latency requirement from the application side, or what would be the maximum amount of time needed or acceptable between the application request till it gets the answer. And one of the typical devices would be a bike lock. If somebody wants to open the bike lock remotely, he pushes the button on his smartphone and he wants to get the answer or the bike open immediately. And those are devices which work with small to moderate latency. And those devices should work either in EDRX or regular DRX mode. The other kind of devices are those metering applications, which basically push the data to the network. It could be a parking meter, a water meter, some gas meters, definitely devices like Amazon Dash button or smoke detectors. Those devices are never reachable by the network, and all the traffic is being initiated by the device itself. And in addition to that, there are some devices in the middle, and they could work in both EDRX or PSM. And to find an answer to that, we came with a threshold which is suitable for devices we know with about 1 hour. For example, if we have a goods container and wants to report to the network every few hours, it is possible to push that information to the network instead of network asking the device every few hours where your data is or where your location is. So, and in this chart, we locate those devices either on the PSM side or on the DRX side. And now I would like to move to Brian for the next slide, and we'll come back with question and answers later on.
Thanks a lot, Dima. So again, recapping on our discussion last time, Gus and Dima have presented a little bit of the underlying technology that's going to offer this great efficiency, this great power efficiency with LPWA. But if we move up to a kind of a macro level and we think about the overall power performance of our LPWA deployments, we can see that the overall power performance depends on two things. First, on the efficiency of the devices and the network that we're using, but secondly, on how efficiently we are using that network to actually push the valuable data we need from the edge to the cloud. So this is what we mean by efficient data management. And there's a couple of considerations to make here. So first of all, we have to make the observation that not all data, not all events at the edge are created equal. Some are likely to be highly sensitive, time-sensitive, highly urgent, tamper detection, for an example. Others might be a more regular meter reading type of event, as Dima suggested earlier. And so how the relative priority of these events means that we want to have some rules at the edge to make intelligent decisions about whether to take this reading and send it right away, whether we could store it and batch it for later, whether we may want to correlate it with another reading or another event, or even just throw it away because it doesn't offer new information. So this business of filtering, storing, prioritizing, correlating, and then finally sending, we call this stream processing. And having the stream processing capability at the edge will allow us to make the best use of our network resources and the best use of our battery. The other consideration to make is that these stream processing rules at the edge are very likely to need to be updated over time. So in a given application, we may start with a bunch of assumptions, but those are going to change over time with new deployments, new regions, new customer demands, etc. So we really want to think about having a way to dynamically update these rules without having to do a massive over-the-air firmware push to our edge devices. We want a way to be able to tweak these in a low bandwidth, low impact way. And this is what we call data orchestration, the central tweaking and updating of stream processing rules. So these are a couple of architectural decisions, considerations around data management. If we move to the next point, this is just to recap some other power optimization considerations in our real world LPWA deployments. So first of all, with battery power, you can't measure, or rather you can't manage what you don't measure. So we want to think about making sure that we have a way not only locally on the device, but actually in our cloud to be able to measure, monitor battery power at the edge. Security. So obviously we're all very concerned and very diligent around the security of our LPWA deployments. And we need to consider that security necessarily adds some level of overhead to our transmission. So security handshakes between device and cloud, software over the air updates, all of this adds some level of overhead. So making efficient use of that and being smart about how we do that is important. And then lastly, location. So many of our applications are going to be centered around location or location information. Obviously, GNSS is a great technology for that, but there are others like cell ID, Wi-Fi ID, Bluetooth tagging, etc., that offer lower power alternatives. So it's pretty good to think about using or employing some of these alternatives to complement GNSS in our LPWA deployments. So with that, I'm going to hand it back to you, Jeremy, for our poll questions.
Thank you, Brian. That's great. Yeah, as Brian says, let's go to our poll. Please remember, your replies are anonymous. So all I would ask you to do is click on one answer, whichever is closest to your own experience here, and we'll see the results immediately after. And the poll question is, where are you at in your IoT journey? Is it answer A, not applicable, I'm just here to learn? Answer B, I'm trying to understand how IoT could transform my product or business? Or answer C, I build connected devices today and I want to know if LPWA is a technology I should be considering. So where are you at in your IoT journey? Let's go ahead and have a little look and see where we are at. That is quite convincing. There is almost 46% saying that they are building connected devices today and want to know if LPWA is a technology they should be considering. So very similar figures for either not applicable, here I'm here to learn, and I'm trying to understand. Gus, can I come to you first? Was that in line with your expectations?
Yeah, pretty much. I think I'm glad to see the that the majority is on the road to building and building connected devices. I think that's a good sign.
Dima, no surprises for you, I guess, there either.
No surprises, and I fully agree with Gus. Great to see people starting implementing this technology.
Anything you'd want to add to that, Brian? It is good to see, isn't it?
It is, and I think just to point out that a quarter of our audience is in the middle category, trying to figure out how all of this technology can help transform their business. So I think that's important as well. I think that reflects a lot of our of the industries out there and of the segments out there.
Okay, well, thank you, gentlemen. It's now time for us to get to some of the questions we didn't get to in our last webinar. And they break down into four key areas. As we've heard already, 5G and LPWA, low power modes, LPWA technology features, and last but not least, data management. Gus, what, in your view, will 5G bring to NB IoT or to LTE-M?
So, well, I mean, just to recap, right? What is 5G? 5G is that system of 5G components where LTM and NB IoT are 5G components. And so really the question is, what components does the release 15 version of NB-IoT and LTM bring? So as you can see at the top there, release 15 is scheduled to be completed in June. Capacity improvements. One of the ITU requirements for 5G is massive LPWA or massive IoT. So 1 million devices per square kilometer is what's required. And so making some improvements to improve capacity. But also you can see there quite a long list of current consumption improvements. This is probably more market driven. The feedback has been, really there is no such thing as too low a current. Everybody wants to get lower and lower. So there's a good 5 major features that are going into release 15 for current consumption. For NBIOT, they're adding the time division duplex capability. So LTM already did have that, so it didn't need that. So this would be for TDD bands. And then also NR, this is the new radio access technology, making sure that LTE-M and NB-IoT both can coexist in sort of an in-band way so you can deploy them together in the same spectrum was really important. So that's been added. So hopefully that answers the question. But if you need more detail on any of these features, just ask the question in the question area, and I will be more than happy to go into any kind of gory details on any one of these features you like. Thank you.
Thanks, Gus. I see also that the questions are coming in thick and fast, which is really good, but please keep them coming. Dima, a question for you. What is required to upgrade to 5G LPWA?
It's a great question. Well, we don't know everything yet. Standards are not frozen. However, they are written in a way that, from what we see, many features on the device side will be able to upgrade by software means only. And the assumption is that all the infrastructure on the network side could be upgraded by software. We don't see people deploying new network, at least not for the IoT. And the commercialization of that is in about 2 to 3 years from today.
Yeah. The next one, I'd like to stay with you, if I may, Dima. Will EDRX and PSM ever get added to LTE Cat 1 and higher devices?
Well, those features are release or category agnostics. The agnostic PSM came with release 12, EDRX was introduced in release 13, and we already see some networks, some advanced network deploying those features very successfully. Not all devices are there yet, but in some countries you could see EDRX devices on Cat 1 network.
So it's already moving forward. I'd like to stay with you on this one too, if I may, Dima, and then I'm going to let you go. Can GNSS work while the modem is in PSM or EDRX mode?
Yeah, it's an interesting question, and it is very much implementation dependent. Some solution would be completely independent within the EDRX and PSM. GNSS could work in parallel with both modes or when device is active. On other, GNSS will work while device in PSM or EDRX, basically in sleep. This can be done by reuse of some of the hardware in the device to further reduce the cost of the devices, which is also very important for LPWA devices.
Yeah, this last one is an important one, and I think this probably ought to be addressed to you, Dima, still. How are LTE-M and NB IoT devices woken up from the network?
It's a good question as well. And it wasn't completely solved yet. It's a difficult question or difficult problem to solve when we see different solutions coming from different areas. One, and the most, and the one I would start with is IP push. Basically, network or cloud could send an IP packet to a device and try to reach it. However, it doesn't really work very well in all networks. To do that, network either has to have a very long session and time out in the NAT, and networks are, or not all networks are built in that way today. The other way is to keep the IP address for the device alive, and or to keep the IP connection alive, and for that device you'll need to send IP packets to the network. And those methods are, I would like to work with both of them, but they couldn't be implemented everywhere, and those are the most natural methods. The other methods are sending an SMS message to wake the device up. The main disadvantage of this method is the cost. If you want to, the cost and the complexity. One, you have to interrupt with the device with some services that can send SMS messages. Not all cloud vendors can do that today. And B, it costs money, and operators charge for that. The other creative method, which is still being used, is a voice call. You could call a device and hang up, and then the device will know that somebody's trying to reach it. It's a way to cheat the previous two. And the last one is a carrier-grade messaging service, which is being defined those days. Google trying to define their own standard, and some networks also providing their own interfaces to wake the devices. Unfortunately, those are not the same across all networks now, and this is not being standardized yet.
So we can expect more on that later, I guess. Dima, thank you. I've got a question about proprietary solutions. Gus, can I come to you? What are the main differences between proprietary and LTE-M or NB-IoT?
Okay, thank you, Jeremy. So, I mean, if we look at proprietary technologies like LoRa, Sigfox, and Ingenue, there's actually a huge difference. I mean, it's probably not enough to even cover today, but I'll try my best here. The main difference is that the proprietary technologies are an unlicensed spectrum. The good thing about unlicensed spectrum is it's free. It's pretty good for private networking too. The bad thing is there's no guarantee of quality of service. And what I mean by that, there's no guarantee of data rates, latency, coverage, battery life, any of those. And that's because the spectrum, of course, is used by many other people, and in general, the interference increases over time. So the performance that you see at deployment might be materially different, for example, 5 years later. Limited ecosystem, obviously by virtue of being proprietary, there's some point in the value chain where there's a single vendor. For example, LoRa, you have single chipset vendor, Semtech. And this not only creates vendor lock-in, but also if that company decides willingly or not to stop producing that chipset, the whole ecosystem, is broken. Also, these proprietary technologies are deployed very differently. They have to, for proprietary technologies, you have to deploy base stations, new base stations, so a greenfield deployment, where LTM and NBIOT, for example, are software upgrades to the infrastructure. This is how some of the big operators like ATT, Verizon, Telstra, many others were able to literally overnight upgrade hundreds of thousands of base stations to support LTM and NBIOT. And lastly, these proprietary technologies in general are really targeting a very low-end application, even simpler than NB-IoT. So they have very limited support. For example, they're really like a messaging type interface. Think of more like SMS, so they don't carry IP data. Also, due to regulatory reasons in the unlicensed band, the base stations have very limited duty cycles, and so they can often not even acknowledge all packets, and certainly can't support large firmware downloads. And also, because they don't support IP messaging, running commercially hardened security protocols like VPNs and TLS and HTTPS are just simply not possible. So there's a sort of a high-level recap of the big differences between the two. Thank you.
Gus, you covered an enormous amount of ground in that, but there's room for us to go into that later if anybody wants more detail. Another one for you, Gus, please. What is the maximum throughput and latency capabilities of LTE-M and NB IoT?
Okay, well, I have the table there, you can see. So these are data rates, or what I call sustained peak data rates. So these are including the scheduling delay, or what some refer to as like a full buffer model. I've seen other people show data rates that don't include scheduling, which I think are really inaccurate because LTM and NBIOT all are scheduled. But for example, if you don't include scheduling, the NBIOT data rate would be like 225 kilobits per second versus the 20 I've shown here for release 13. So there's a massive difference, but really the numbers I'm showing here I think are accurate. These are what you can measure, even in the very best coverage. So for LTE-M, those are for half duplex devices, just to let you know. The standard does support full duplex devices, but nobody really builds those today, so I didn't include those. You can also see there's two rows, one for release 13 and 14. You can see there's a substantial increase, especially in NBIOT data rates for release 14. And as I mentioned earlier, release 14 is standardized in June 2017, so expecting commercialization of release 14 in early 2019. The latency numbers you see on the right are assuming the device is in what they call connected mode. This means the device has sent data within the last sort of 10 seconds. If the device hasn't sent data, in the last 10 seconds, it would drop into what they call idle mode, and then there needs to be a transition from idle to connected, which takes, as you can see on the last few bullets, a fair bit of time. So that'd have to be added to the top right numbers as well, if that was the case. So hopefully that answers the question.
Thanks, Gus. And the last question for now to you, Gus. Is NB-IoT suitable for mobile applications?
Thank you so much. I really like this question because, as you probably heard me say in the introduction, well, NB-IoT has limited mobility, but that's not really a very useful answer. But like all good questions, they're not necessarily super simple to answer. So the first thing to understand about NB-IoT, like LTE and LTE-M, there are these two states I mentioned, idle and connected. So idle is when the device is not sending any data. So for NB-IoT, when you're in that mode of not sending data, the device is always listening and making sure it's going to listen to the closest base station. But once you start sending data, the device, due to simplicity, no longer tracks neighbor cells. So all it's going to do is look at the serving cell. So what that means is, for example, when you start a connection, you're going to be connected to the best base station. But if the connection lasts, for example, a minute, and you're highly mobile, there's no way to hand off to any other base stations. So eventually you'll get very, very far from that base station. And that has a lot of negative consequences. And one of them is that you end up using a lot more network resources because, of course, your coverage is limited. You're not your real coverage, but because you're so far from the base station. And this can be quite dramatic, like hundreds of times more resources. And same with on power consumption. Because you're having to go past that link budget, it takes a lot of power. In the very worst case, when you end up dropping the connection completely, you end up having to actually restart the whole transaction. So you might be 90% done your transaction, and the way the network works is you actually end up having to start from scratch. So that, again, uses more resources and more power. So the net of it is, NB-IoT is okay for what I call slow mobility, pedestrians, bikes. Definitely not for cars, and also not for streaming. You got to keep the connections short. So hopefully that answers the question.
Thank you. It does, Gus. Brian, a few questions came through that I'd really like you to tackle if you would. The first of which is, what communication protocols do LTE-M and NB-IoT support?
Yeah, great question. Thanks, Jeremy. So Gus mentioned a few moments ago that the LPWA, cellular LPWA, are IP-based. And so as a result, we get the suite of protocols that we are used to in IP networking. So normally in LPWA, we're thinking about we're thinking about low bandwidth. We're thinking about efficient messaging. So protocols like lightweight M2M and MQTT are increasingly seen as standards for communicating on LPWA networks. We do support TCP/IP as well, and Dima mentioned SMS.
And
hopefully that answers
also, Brian, yeah, it does. The question I wanted to get to now was, how does data orchestration complement LP1 to improve battery life?
Yeah, so this is a great question, and I think we're back here on the macro level. So again, starting with our fundamental rule that regardless of the efficiency of the network, transmitting data still consumes energy. So we're trying to do that as efficiently as possible. And maybe the best way to think about this is to illustrate it by way of example. So the example that we have here is a medical lab tote. So a little sidebar to explain what that is. Most of us are familiar with medical lab services where we have to go and get a blood sample, for example. And often those samples are transported to somewhere else for testing. And so they're usually transported basically in a cooler. And obviously those samples can be very sensitive to changes in temperature and in expired time before processing, et cetera. And today those aren't tracked. In the majority of cases, there's not a lot of visibility to those samples. So this is a great example of where LPWA can make an impact. So with that explanation, then how does this relate to data orchestration? So we can imagine a case where this lab tote goes from medical clinic to vehicle, from vehicle across to a different part of the city, and then from there into a hospital or into a research center where it's very deeply embedded into the building. And during that time, the signal strength is going to change dramatically. And when signal strength changes, so too does the power required to transmit data. So what you really want, if you want to optimize power over the life cycle of tracking these totes, is a way to make the right decision about when to send different events based on your knowledge of signal strength. So an example, a simple temperature reading or a location reading, maybe you do that once every 10 minutes or so. Maybe when you've got really poor signal strength, you can hold on to those readings and wait until you've come into better coverage. Going the other way, though, if you have a light sensor which is tracking potential tampering with these packages, clearly that's an alert. We want to send that right away. So again, the business of data orchestration is having the knowledge of the context of the data and being able to use that knowledge with the different variables to understand how you can send the right data at the right time with the right priority. So hopefully that's an illustrative example.
Thank you, Brian. And the last of the questions from our previous audience that I want to put to you, Brian, if I may, is do you expect IoT applications to leverage artificial intelligence engines as a way of optimizing data over time?
So awesome question, and great that the audience is looking forward a little bit. So the short answer is yes, and we do expect AI to have an impact here. What we know for sure is that regardless of the model, we'll need a distributed approach to deploy the machine learning in the cloud to tune our model and then deploy inferences at the edge that can actually make use of that. What we don't know 100% is exactly what use cases we're going to leverage AI for in the context of data management. But there's a couple here which I think hold a lot of promise. So the first here is basically message content analysis. So we talked about understanding the priority of different messages. We're all familiar with modern cloud-based email systems, which basically prioritize messages for us and even suggest responses. So imagine this in an IoT context where your edge device is actually making inferences on the data that it sees to decide how important, what priority should be given to a given event. So that's one pretty interesting one. Coming back to security, so we talk a lot about anomaly detection in the industry, and that makes a lot of sense. Usually we talk about statistical anomaly detection, meaning, if I have thousands of devices deployed and they're all consuming, for example, X data rate, if I see one or two devices coming way outside that threshold, I can identify them as statistical anomalies and take an action. So that works great when you have very regular patterns of behavior, not so well when you have more subtle changes. And so when we come to security, a lot of security attacks have more subtle patterns of behavior and are harder to detect with statistical anomaly detection. This is where artificial intelligence comes in, is these abnormal patterns. And so to me, that's a pretty exciting area of research and development. And then lastly, again, big picture here, we've talked a lot about making the right decision of when to send data and when to process data at the edge. And that's something that if we think about on a macro scale, having an AI view of arbitrating whether or not data should be processed at the edge or be sent to the cloud for processing at real time is pretty interesting. So that's kind of even further out, but something that I think would be very promising.
Brian, thank you. Well, that's excellent. We caught up with the key questions that arose from the first webinar. Now it's time to put your queries to our panel. I can see you've been sending us more and more questions, which is great. Please keep them coming. Let's see what other questions have arisen today then. We have a well-known IT process firm here asking what is the limit for data packet size in category NB1. Would you care to take that, Gus, please?
Yes. Yeah, I can take that. So for NB1, but also LTE-M, when you use some of these small data packet optimizations, the one I'm thinking of is it's called data over network access stratum signaling. You end up having to fit inside a control plane message. And so that's the limit. And the limit is, simply put, 1,600 bytes. So the short answer is when you're using these small data packet optimizations, then your limit is 1,600 bytes. Strictly speaking, an operator could deploy a network that didn't use that, and then there is no limit. But when you're using that small data optimization, which is typically enforced for NBIOT, then that's the limit.
Thanks, Gus. There's a good question here from a chip technology firm. Dima, I'd like to put this to you, if I may. They want to know, will NBIOT support firmware over the air, and how long does it take? I know that it's been touched on earlier. Can you give us a little bit more detail?
Yeah, I can answer that. I think most of the devices today will require firmware over their upgrades, especially if you consider a deployment over 10 years, pretty much mandatory feature. And I believe most devices from most vendors will support firmware over the air. The caveat is, however, is how long does it take? And as we have seen in Gus' slides, if the downlink throughput is 27 kilobit per second, and for example, downloading a 200 kilobit image or 200 kilobyte image could take many tens of seconds or minutes. And this will consume a significant amount of power. So I think, yes, there will be NB-IoT FOTA. It's mandatory, but it will consume power and people will have to use it very carefully.
There's another question here from a chip provider. Brian, I'd ask you this, if I may. Why is uplink throughput more than downlink throughput in both Cat-M and NB-IoT? Is that one that you'd be able to give an answer on?
I could try, but I'm actually going to pass that one over to Gus from a networking perspective.
Yeah, I'll answer that one. So it's without a lot of diagrams, it's difficult to explain. But if you think about, because these are half duplex devices, and when you try to send and receive, the thing about it is when you're doing a downlink, there's more transitions because you have to do an acknowledgement in the uplink. So there's just more scheduling delay when in the downlink. You basically have to get a grant and then wait for the data, and then you get the data, and then you have to wait for the acknowledgement, and then there's also some time before you can send the next grant. So all of that sort of adds, where in the uplink it's slightly less. I mean, the differences aren't huge. But for example, like in release 14, you see for LTE-M, the data rate doubled in the downlink. And one of the things that they did there was we basically created the ability to do a group acknowledgement. So instead of acknowledging every single transport block and having to do this transition, we changed it so you can basically acknowledge multiple packets with one go, and that's why the data rate is basically doubled. And so the beauty of that is you get this doubling effect, of course, across all coverage levels. So that's sort of how that works. So hopefully that answers the question. Now, without diagrams, it's sort of more difficult to explain, but hopefully that makes sense.
It does make sense. Thank you. Gus, I'll stay with you for the moment, if I may. There's a question from a multinational telco here. What would be the protocols used to send unsolicited data to a device in EDRX? Is that something that you could give us an opinion on?
Well, actually, I think this is the exact same question that Dima answered earlier. I mean, unsolicited data is basically you're trying to, send a message from the cloud to a device. And Dima did talk about that already. Maybe I will just answer it sort of the same way. I really think you did a good job, though. But, I mean, you can send, with EDRX, you're waking up, or DRX, you're waking up in a certain interval. When you wake up, you'll listen to see if there's a packet for you, right? And that could be an IP packet, it could be an SMS, it could be a voice call, doesn't matter. Those techniques are, as Dima mentioned, IP, especially if you can get around the network access translation, the NAT timing issues, that's the best way to go. But otherwise, you fall back to SMS and worst case voice calls. But with IPv6, I think this is maybe one of the things Dima didn't mention. With IPv6, the ability to assign static IP addresses and get around the NAT issue will virtually, go away. So I think that's one of the longer-term solutions that people are looking at for unsolicited downlink.
Thanks. Dima, I'm going to throw this to you, if I may, and feel free to pass it off if it's not best directed to you. But it's a question from a leading North American telco who want to know what would be a good set of questions to ask potential customers for selecting PSM and or EDRX to extend battery life.
I think it's also related to the slide we had earlier. The first criteria I would ask is, what is your application? Is it reachable by the network, or is data coming on, or is it device-initiated data? This would be the first criteria. If the answer would be device never sent data by its own and always waiting for the query by the network, then probably I would lean toward EDRX. On the other hand, if devices, all the data is being initiated by the device, I push a button and it sends the data, then I would lean towards PSM. And the other criteria I also would look at is how much data we send overall, or how frequently we send the data. And again, if data is sent if data is sent more frequently than the reachability period of the device, then I also would lean towards the PSM. This is the upper side of the graph we had, of the figure we had earlier.
Okay, thanks, Dima. And a question for Brian. Somebody wants to know, when will NB-IoT and LTE-M be available in North America, Europe, and Asia? And I know this has been touched on a little bit. Could you give us a little bit more than we've had to discuss on this already?
Yeah, absolutely, Jeremy. So Very good question, obviously relevant for everyone here. So let's break this up a little bit into what we have today and then what we see at the end of 2018. So the simple version is there's probably enough for most people to start trialing now and to get ready for full commercial deployment by the end of this year. To be a bit more specific, if we look at, first of all, the current state in Europe, we're sort of below 50% coverage right now. Most of that is NB-IoT based, with a few LTE-M networks in Benelux and Turkey mainly. And so that's where we are today in Europe, a little bit patchy. Same thing in Asia, NB-IoT in China and South Korea, Australia, as is often the case, leading the charge with both LTE-M and NB-IoT present. And in North America, pretty solid LTE-M coverage right now in the United States and Mexico. So again, if you follow one of those geographies, chances are you can start to trial this technology now. Now, important to recognize, by the end of 2018, the situation is very dynamic. Of course, there's no authoritative source to say exactly when all of these networks will get turned on, but based on I would say, a very good knowledge of the market, our view is that by end of 2018, majority of Europe, Russia, East Asia, including Japan, China, etc., Australia, New Zealand, North America will be well covered, both with Cat-M and NB-IoT. And in addition to that, we're going to start to see coverage in Southeast Asia. So India as an example, South America and Brazil and Argentina, and also Middle East and Africa. So by end of this year, truly a global coverage. I hope that answers.
It does. Thank you.
And I just, if I may, Jeremy, I wanted to chime in on the question earlier from Dima that Dima responded to, just in terms of the PSM and EDRX. I think Dima answered the question well. The only thing I'd add is that, again, per our poll earlier, customers sometimes when they're speaking to us often don't have a clear view of how all of this technology can impact their business. So it's pretty important in those cases to start, and I always like to start with an understanding of not of the device side, but actually of the application side, and really trying to paint a picture of what is the application going to look like, who are the users, all of those good things. And from there, it's much easier to infer what the right data model is, and then from there, what the right edge strategy is. And so really that's an important piece of the puzzle as well.
Thank you. Thanks, Brian. Dima, can I put this one to you? Somebody in Eastern Europe is asking, is LPWA operated also on IPv4?
I think you actually not quite an expert. Maybe Gus can add on if I'm wrong. You could do IPv4, but most of the network would be IPv6.
Gus, anything to add on that?
Yeah, I mean, it's definitely network dependent. So I think that some networks are dual mode, IPv4 and v6. And then, as Dima mentioned, I think there's definitely a push to go to IPv6 as fast as we can for this technology, given we're trying to, be a massive IoT that's where IPv6 really can make a big difference.
Thanks. I'm going to keep you, if I may, for a little bit longer, Gus. Do you have advice for different verticals as to how they should deploy EDRX and PSM, depending on their use case? This from a leading association.
So let me make sure I understand. I'm not sure I quite understand the question. Do you have advice for different verticals, how they should deploy? Well, I mean, this sort of comes back to really what Brian and Dima said. I mean, it really depends on the application. I mean, the way I look at EDRX and PSM is if you need to be reachable, I call it online, then you need to be in EDRX. If you're kind of more of an offline mode where you don't need to be reachable, then you can be in PSM. And then if you want to be reachable, the question is how reachable? Like with what type of latency? Do you mind if somebody waits 10 seconds or 15 seconds or maybe even 80 seconds before they can reach you? Or do you need to be reachable within a second? If the answer is you need to be reachable within a second or less, well, then you need to just use regular DRX. Of course, there's a power consumption hit for that. The longer you're willing to have your, that latency be, the better your battery life is going to be. So maybe that's a bit more color on sort of the same kind of question.
There's a question here. Thank you, Gus. There's a question here from a leading German-based IT service provider, and I'd like to put this to you, Dima, if I may, but there may be aspects of this that Brian would want to tackle, and that is about NB IoT Release 13. The questioner wants to know, will it get automatically enhanced to Release 14 when it's released, or is it going to be done with a firmware upgrade manually? Dima, is that something you could tackle?
Yeah, I can answer that. And it's similar to 5G as we spoke earlier. Networks will get an upgrade. Selected devices will get an upgrade over the air, unless they're already deployed by Release 14. However, most of the devices are Release 13, and they will have to get upgrade over the air if they're capable to.
Thank you. Gus, I'm going to come back to you because this question refers back to one of your earlier answers. He says, I recall the transport block size was 1,000 bits for NB-IoT, but Gus mentioned 1,600 bytes. Can you verify, can you explain, I think he means, why the difference?
Yeah, that's actually, I'm so glad you came back to that question because I want to clarify. Correct. So the transport block size is 1,000 bits, but that's really at the very physical layer. That's not at a layer of where you send those. You end up basically concatenating those 1,000-bit sections into the 1,600 byte sections. Even LTE-M, by the way, the transport block size is 1,000 bits. That doesn't mean you can only send 1,000 bits. It just means that, and that's where your data rate, that 1,000 bits relates a lot to the data rate. It means for LTE-M, for example, the most you can send is 1,000 bits in 1 millisecond, or what they call 1 subframe. So that's where that 1,000 bits, that doesn't relate to the maximum packet size that you can send. So hopefully that clears it up. There's kind of different layers there. The physical layer, yes, 1,000 bits, but completely unrelated to sort of an application layer message size.
Understood. Gus, thank you. Brian, I've probably got time to squeeze in 2 more questions. Can I ask you to be quite brief on this one? Questioner wants to know, where can we get a development board?
Oh, right. Okay. Great question. I can be very brief. Please go to mango.io. That's mangoh.io. And what is that? That's an open source hardware reference platform sponsored by Sierra, but with it's a great development board and development platform and open source community for prototyping. So mango.io.
Thank you, and thanks for your brevity. There's a question, and this will, I'm afraid, have to be the last one. Dima, I'm going to come to you, please, but if you want to hand it off to somebody else, then feel free. The questioner wants to know what happens when the PSM timer T3412 expires. Does the module wake up into idle mode automatically?
I'll be very brief. It will wake up not to idle mode, but it will transmit something called a time area update message to the network, and this would be an opportunity for the network also to add some traffic or for device to send traffic, but it does not wake up into the idle mode.
As brief as you promised. Thank you very much, everyone, for adhering to the time so that I don't get my knuckles wrapped, and it's very good of you to have taken so many questions. Thank you, gentlemen. The aim of this webinar has throughout, as you know, been to help everyone try and deploy a low-power, wide-area application. And I guess we talked through many of the challenges, as well as, in many ways, how to overcome them. Sadly, that is all we have time for. Please don't forget to bookmark our website at iot-now.com. You'll find the latest news there, plus, of course, the usual videos, blogs, events, and interviews. And most importantly, you can stream this webinar from the site tomorrow. You'll find a link also on the website to part 1 of this webinar, and that is again at iot-now.com. It's also important to say that a recording of today's proceedings will be emailed to all registered delegates. So you can't miss out. It's coming to your inbox, and it's also available if you go and look on our website. In the meantime, it just remains for me to say a huge thank you to our speakers, Gus Voss of Sierra Wireless. Great to have your expertise, Gus.
All right. Thank you for having me.
And thanks to Dima Feldman at Altair Semiconductor. We really appreciate your time, Dima.
Thank you for having me.
And also from Sierra Wireless, Brian O'Flaherty Wills. Many thanks, Brian.
Thank you very much, Jeremy.
And most of all, ladies and gentlemen, I want to thank you for joining us around the world. Keep safe. We do really appreciate the time you've spent with us. From everyone here at IoT Now, enjoy the rest of your day. Bye for now.